You know, what does it really mean to heat something up? Seems pretty simple, right? But when it comes to gases, things get a little weird. It's actually a bit of a puzzle. What if I told you that it can take two totally different amounts of heat to get the exact same change in temperature? Sounds impossible, doesn't it? Well, let's dive in and unlock this secret. So why is heating a gas so much more complicated than, say, heating a solid block of metal? It's because it's not just about making the molecules inside zip around faster. There's this hidden cost that we have to account for, and it changes the entire equation. Okay, to really get to the bottom of this, let's set up a little thought experiment. Imagine we've got two cylinders of gas. They're completely identical in every way. Well, almost. There's one crucial difference. The cylinder on the left, its piston is locked solid in place. But the one on the right, its piston is totally free to move up and down. Now, here's our goal. We're going to add heat to both of them, and we want to raise their temperature by the exact same amount. All right, so here's the million-dollar question for you. Which one do you think is going to need more heat to hit that target temperature? Is it the one with the locked piston or the one where the piston is free to move? Go ahead, take a guess. Because the answer? Well, it reveals a really fundamental principle of thermodynamics. Okay, the solution to our little puzzle lies in the fact that there isn't just one way to measure the heat capacity of a gas. There are actually two. We call them CP and CV, and they are the absolute key to understanding this whole cost of expansion idea. So, first up, let's look at our locked piston cylinder. Pretty straightforward, right? The piston can't move, so the volume of the gas is held constant. The amount of heat you need in this specific situation is called the molar specific heat at constant volume, or just CV for short. And you know what? In this scenario, it's beautifully simple. Every single bit of heat energy you pump into that cylinder has only one job to do: make the gas molecules inside move faster and faster. That's it. This is what scientists call the gas's internal energy. So all the heat you put in goes directly, 100%, to jacking up that internal energy. No energy is wasted or spent on anything else. Okay, now let's switch gears and look at our other cylinder, the one with the free piston. What happens here when we add heat? Well, the gas gets hotter and it expands, pushing that piston up. And by letting it expand, it actually maintains a constant pressure inside. The heat we need for this process is described by a different value, the molar specific heat at constant pressure, or CP. See, in this case, the heat energy we add suddenly has two jobs to do. Part of it still does the same thing. It raises the internal energy, making those molecules zip around like crazy, but another part of that energy gets spent doing work. I mean, literally, physical work by pushing that piston up against the pressure of the atmosphere. And that is the hidden cost we were talking about at the beginning. And this, right here, is the absolute core of the whole thing. The source material puts it perfectly. The heat that is added to the gas goes only partly into heating the gas, while the rest is transformed into the mechanical work performed by the piston. So because some of your precious heat energy is being siphoned off to do work, you have to add more total heat just to get the same temperature rise. And that means, drumroll please, the cylinder with the free piston is the one that requires more heat. Okay, so we've established that CP is always bigger than CV. The free piston always needs more heat. But how much more? Is it just some random amount that changes all the time? Absolutely not. Turns out there's a beautifully simple, elegant equation called Mayer's relation that tells us exactly what that difference is. Now, don't let the math on screen scare you. The derivation might look a little intense, but the idea behind it is actually super simple. We're just starting with that basic principle we already talked about. The total heat added, which is our CP term, has to equal the heat that actually raises the temperature, our CV term, plus the energy used to do work. And for an ideal gas, that work term just so happens to be directly tied to the universal gas constant, which we call R. So you do a little bit of algebraic magic, you cancel some things out, and you end up with this stunningly simple result: CP equals CV plus R, or CP minus CV equals R. The extra heat you need, it's not some mystery number. It is exactly the universal gas constant. That's Mayer's relation. So cool. All right, so we know that CP and CV are different, and we even know they're different by exactly R. But to understand why they have the specific values they do, we have to change our perspective. We need to zoom way, way in, from the macroscopic world of pistons and cylinders down to the invisible world of individual molecules. And when we get down to that level, the key concept we need to grasp is something called degrees of freedom. The easiest way to think about this is like this. Imagine every molecule has different ways it can store energy, kind of like separate little bank accounts. It can store energy just by moving from point A to point B. That's called translation. It can store energy by spinning or tumbling. That's rotation. And if it's made of more than one atom, it can store energy by having its atoms wiggle and vibrate back and forth.
So let's take the simplest case, a monatomic gas like helium or argon. It's just a single, solitary atom. Think of it like a teeny tiny billiard ball. It can't really spin in any meaningful way, and there's nothing for it to vibrate against, so it only has 3 places to put its energy, moving left-right, up-down, and forward-back. 3 degrees of freedom. This gives it a specific heat at constant volume, a CV, of 3/2 R, and because we know Meyer's relation, we just add R to that and we know its CP must be 5/2 R. Simple.
Okay, but what about something a little more complex? A diatomic gas, like the nitrogen and oxygen that make up most of the air we're breathing right now. These molecules are shaped like tiny dumbbells, 2 atoms stuck together. So they still have those 3 ways to move through space, but now they can also rotate. They can tumble end over end or spin like a propeller. That adds 2 new bank accounts for energy, giving them a total of 5 degrees of freedom. And because there are more places to store that heat energy, its CV is higher. Now it's 5/2 R, and its CP is, you guessed it, 7/2 R. And now for a really fascinating, mind-bending twist that comes to us from the world of quantum mechanics. You'd think a hydrogen molecule, which is diatomic, would always have 5 degrees of freedom. But at very, very low temperatures, it just doesn't have enough energy to get itself spinning. The rotational bank accounts are effectively frozen shut, they're locked out. So under these extreme conditions, it behaves just like a simple monoatomic gas, with only 3 degrees of freedom. It's a wild, real-world example of weird quantum rules having a direct impact on the macroscopic properties we can measure. So we've talked a lot about CP and CV and how they're connected to the very structure of a molecule. But now we're going to look at what happens when you divide one by the other. We're going to look at their ratio. And this ratio, which gets the Greek letter gamma, is honestly one of the most important and useful numbers in all of physics and engineering. So what is gamma? It's simply CP divided by CV. That's it. But because both CP and CV are directly tied to those degrees of freedom, this single number acts like a powerful fingerprint for a gas. If you tell me the gamma of some mystery gas, I can tell you if it's monatomic, diatomic, or something even more complex. It gives us a direct window into what the molecules actually look like and how they behave. So why should you care about this ratio? I mean, why does it matter so much? Because it shows up everywhere in the real world. It's absolutely essential for figuring out what happens during the compression stroke in a car engine. It's a critical part of the formula that gives us the speed of sound through that gas. Engineers use it to calculate the efficiency of everything from power plants to jet engines. Seriously, this one little number is a total giant in the world of applied physics and engineering. You know, think about where we started. We had a simple question about 2 cylinders of gas. And that journey took us all the way down to the quantum world and then all the way back up to calculating the speed of sound. And it all hinged on whether a tiny molecule is free to spin or not. It really makes you wonder, doesn't it? If a molecule's freedom to just wiggle can change something as fundamental as the speed of sound, what other invisible microscopic rules are secretly shaping the big macroscopic world that we see and experience every single day?